Read the question carefully. Basically, we want to construct a fence around a rectangular region, around a rectangle of area 1225, and we need to find the dimensions to minimize the amount of material needed. So when we construct fence that goes around the perimeter, okay, so let the dimensions be x and y. So this is, let's say, x here, and this is y, okay, and area, so the area is fixed, 1225 square feet. That's the constraint. So the constraint here is area 1225. So x times y equals 1225. Now we can solve for one variable. Let's solve for y. So divide both sides by x. So y equals 1225 over x. Let me say equation 1. Later, when we find x, we come back here and find the corresponding y. Okay, so next thing we want to optimize, in this case, minimize the amount of material needed. So minimize amount of material needed. So objective function. So the material goes around the rectangular region here. That means x, this is y, this is x, and this is y. Okay, this is way off. This is y. So x plus x 2x, and y plus y 2y. 2x plus 2y. That's where the material goes, and that's our objective function. It's like perimeter. That equals 2x plus 2y. We can use p if we like. Now we need to write this objective function in only one variable. So use equation 1, replace y by 1225 over x here. So this is 2x plus 2 times 1225 over x. We can multiply, don't have to, but let's multiply anyways. 2x plus, this is 2450 over x. Okay, this is the objective function. Now we want to optimize. In this case, we want to minimize this. So let's find the derivative of this function. Then derivative of 2x is 2 plus derivative of 2450 over x. So we can do in this way, 2450 over x. To find its derivative, we can use the quotient rule. In fact, okay, we can use the, and when we use the quotient rule, we get negative 2450 over x squared. Okay, so that's negative, makes this plus, minus, okay, minus 2450 over x squared. Okay, we don't have to use quotient rule. By the way, 2450 over x is same as 2450 times 1 over x is x raised to negative 1. Now we can use the power rule. So 2450 times, it's like x to the n, and its derivative is n x n minus 1. So 2450 times negative 1 is negative 2450 times x raised to negative 2, and put that on the bottom, then we get this. Okay, anyway, this is the derivative. Now we have the derivative of the objective function. Now the next step is to find the critical numbers. So we set the derivative 0. Okay, so set derivative 0. That implies this quantity is 0. So 2 minus 2450 over x squared equals 0. Now we need to solve this equation. I mean, there can be a couple of different ways to solve this. So this is negative fraction. I want to add both sides, basically move this over. So this implies, so let me write over here, 2 equals, this negative means add this fraction to both sides, 2450 over x squared. And whenever we have one fraction in the right side, we can make 2 over 1 another fraction. we can cross multiply. So that implies 2x square is 2450 divided by 2. We are trying to isolate x, okay? 2450 divided by 2, so 1225. Now take square root both sides. Take square root of 1225, that's 35. So x equals 35 optimizes, in this case minimizes. But how? Why this minimizes? So we can do the sign chart if we know the bounds for x, or we can find the second derivative. Let me find the second derivative, okay? To check x equals 35 minimizes or maximizes, because we have only one answer, so it will minimizes the fencing material amount, because we want to minimize the fencing amount. Let's find the second derivative. So we have first derivative here. Let's find its derivative one more time. So second derivative is, derivative of 2 is 0 minus, now we can use quotient rule again. So that will be then okay, just use the quotient rule, or you can move x square to the top, that becomes x raised to negative 2, then do the power rule, same thing. So this is 0, negative, negative, positive, so it will be 4900 x over x to the fourth, which is x cubed. Okay, so this one does not count 0, and this negative and minus becomes plus. 2 times 2450 is 4900, and 1x cancel from top and bottom, x cube. So this is the second derivative of this one. Now we want to evaluate this at 35, because we are trying to check if 35 makes the fencing amount minimum. Okay, so let's do that. Now at x equals 35, what happens to the second derivative? Second derivative is just plug in 35 here, so 4900 over 35 cube. I don't have to know the exact amount. This is pretty much a positive number, okay? It's a positive number. So when second derivative is positive, the curve, the function is concave up. So our function is concave up. So this critical number will be the minimum. So we get the function concave up. So that means x equals 35. This critical number does the minimum, makes the function minimum, and that function is the objective function. So is minimum. This minimizes. This is not the minimum value, but this minimizes whatever the objective function is. Now we go back and write down the final answer. So we were asked to find the dimensions x and y, and we found x to be 35, and we also tested that is indeed it will minimize the amount of material. Now x is 35, and we need to find y. That y is found from this constraint. So y is 1225 divided by 35. 1225 divided by 35. So finally we write, thus the dimensions, okay, for minimum amount of fencing are x and y, that is x is 35 and y is, go to the constraint, that's 1225 divided by 35. So 35 inches or feet, this is feet, okay? So 35 feet, and 1225 divided by 35 is also 35. So 35 feet by 35 feet. So you can write 35 feet by 35 feet. Final.